With that, we're going to hear our first presentation today from Brian Lockwood, who is a hydrogeologist and general manager for the Pajaro Valley Water Management Agency. Pajaro Valley Management Water Agency is a state-chartered water management district formed to efficiently and economically manage existing and supplemental water supplies in order to prevent further increase and to accomplish continuing reduction of long-term overdraft. Brian has provided technical analysis, review, and oversight for basin management plan programs for the last 8 years, and his work has included capital improvement projects, aquifer recharge, recycled water, groundwater quality, seawater intrusion, conjunctive use, and a whole lot of other things. Basically, he's doing it all. Lockwood is also serving on a Sustainable Groundwater Management Act advisory panel that is being administered by the California Department of Water Resources. So we're very honored to have Brian with us, and take it away, Brian.
All right, thank you. Thank you for that warm welcome, and it's a real honor and a pleasure to be here today. And yeah, when you work at a tiny agency, you end up doing a whole variety of things. So we do what it takes to make the agency run. It is great to be here, and I'm still feeling the jazz from Jerry Spinelli earlier. And that was really great. I didn't realize that secret talent that Jerry had. During my talk today, I'm going to, start off with just acknowledging right off the bat that the work I'll be presenting has been developed by a whole team and has been provided direction from the Pajaro Valley Water Management Agency Board of Directors, who have had to make some tough decisions over the years to keep this agency moving in the right direction. I will tell you a little bit about the Pajaro Valley itself, set up the state of our groundwater basin, touch on our water resource management activities with a little more focus on our MAR projects. And hopefully some of this will cue up Andy's talk, which will follow me, Professor Fisher. And that will conclude the talk. So Pajaro Valley, we were formed in 1984 as an act of the California legislature. We're a special act district. 1984 predates the Sustainable Management Act, Sustainable Groundwater Management Act, by 30 years. And so we do a lot of the things that SGMA had wanted these new groundwater sustainability agencies to do, but we were doing it long before SGMA was established. We are multi-jurisdictional. There's just one incorporated city within our boundary, and that's the city of Watsonville. But we include parts of Santa Cruz, Monterey, and San Benito counties. And I'll dive into more of what we do as I go through the presentation. We are located, in Central California, along the coast, right near Monterey Bay. And this slide here shows in dark black the statutory boundary of the Pajaro Valley Water Management Agency. And then in dashed blue, the watershed boundary for the Pajaro River, which gives us our name. And we are just the tail end of the larger, much larger watershed, which requires us, and is a good thing, to be in coordination with our neighboring water agencies upstream in the watershed. We are governed by a 7-member board of directors. This was established in our agency act. We have 4 of the directors, those whose names are shown on the divisions A through D on the map, are by election. The other 3 directors are appointed, and they have to earn a majority of their income through agricultural activities. So the Santa Cruz County Farm Bureau and the Monterey County Farm Bureau makes recommendations to the Board of Supervisors and to the City of Watsonville to appoint the directors. Elected directors serve for 4 years and appointed for 2 years. And this provides this information because there's been, a lot of information with groundwater sustainability agencies, and the governance structure is important to what we do. I've got 2 slides on the Sustainable Groundwater Management Act to put it into perspective for the agency. SGMA, as I said, was adopted in 2014, about 100 years after the state of California adopted law for managing surface water. And it requires critically overdrafted groundwater basins, such as the Pajaro Valley Basin, to achieve sustainable resources by 2040. And the stick in this is that if the State Water Resources Control Board has the authority to come into groundwater basins and take control if individual basins are not able to achieve sustainable resources. And that's a really big deal. Here in the valley, not everybody likes Pajaro Valley water necessarily, but they would prefer to maintain as local control as possible. So PV water is better than, say, county control, which is better than state control. So we've been working diligently for the last 36 years to achieve sustainability. So this slide just sort of runs down a few of the things that we've done. One of the big things that SGMA does is it requires groundwater basins to develop groundwater sustainability plans. These are the plans on how each basin will achieve sustainable groundwater resources by the deadlines of 2040 or 2042 if you're considered a medium or lower priority basin. We have developed what we had called basin management plans beginning in the early 90s, and then have adopted them on about a 10-year or so cycle, the most recent one in 2014. These plans provide direction to staff on the kinds of projects and programs we're going to develop to achieve sustainable resources. Our board of directors elected to become a groundwater sustainability agency in the fall of 2015, and then we worked with our neighboring agencies to conduct a basin boundary modification in 2016. And this slide here shows a difference between the statutory boundary of PV water and the groundwater basin boundary as it stands today, given the modifications, which is shown in blue. And, you know, sometimes what happens in Sacramento doesn't necessarily match hydrologic conditions. And we see this, you know, really all around the country. We don't have the counties that are defined by watershed lines. They're defined by political lines. And that's what this black line was intended to be. This shaded area shows the extent of our hydrologic flow model that we use for basin management activities and to evaluate the state of the basin. We submitted our basin management plan and a host of other documents to the state Department of Water Resources in 2016 as an alternative to a groundwater sustainability plan. Because our most recent plan was adopted in the spring of 2014 and SGMA was passed in the fall of 2014, they didn't match exactly what groundwater sustainability plans were supposed to have, but the intent is still the same, to achieve sustainable resources. It took 2.5 years, but in the summer of 2019, DWR provided notice that our plan was approved. And now we're working on the first of what will be an ongoing annual cycle of updating the plan every 5 years. So, you know, having an alternative to a groundwater sustainability plan leaves a lot of people questioning as, you know, what is it? And so our alternative, the heart of it is our basin management plan, which evaluates the state of the groundwater basin and provides a recommended list of projects and programs. These are developed by a 21-member stakeholder that provided input to our process. We also have a programmatic EIR that certified the program. And then we have our modeling report that we collaborated with the USGS to build, and we started that effort in 2005 and are still working on it each and every year to improve the model as a tool and continue to refine its accuracy and develop updates to it. Our Agency Act provides the governance structure that I touched on earlier. And then our salt and nutrient management plan, these 4 documents round out the bulk of the alternative. The salt and nutrient plan describes the water quality aspects of the basin, whereas the basin management plan is more focused on supply. And then in addition, there's a host of other documents we submitted as well, things like our cost of service study, which serves as the basis for our rate setting effort, and our facilities plan and quality assurance plan and peer-reviewed journal articles that we've developed. So I'm going to take a few slides here to talk about what is the Pajaro Valley Basin, what happens here, and then we'll move into managed aquifer recharge. This is an agricultural basin, and we have the great pleasure of working with folks like Andy Fisher and his colleagues at UC Santa Cruz, and we've collaborated with Stanford University and with the RCD of Santa Cruz, and we've had the pleasure of working with Jerry Spinelli on our agricultural conservation program. And that's important because there's about 28,000 acres of irrigated agriculture in the valley, which will generate between $900 million and about $1 billion on a year, depending on how the crops do. And the crops are predominantly berries, strawberries, raspberries, blackberries, and vegetables. And they have a symbiotic relationship with one another, rotating through from strawberries to vegetables. Much organic property here in the valley. And predominantly all of the water that's used to bring the crops to production is coming out of the groundwater basin. So there's about 2,000 or so wells in the valley, and we put meters on those that pump and serve the agricultural activities. So we have a really good sense of how much water is being pumped for ag and for residential uses. And so this slide summarizes that, where agriculture is using about 85% of the water, and the municipal and industrial uses are about 13%, and the rural residentials are about 2% in total. We do have a water recycling facility that's been producing more water each and every year, and I'll touch on that. But the results of having meters on the wells since about the mid-90s does allow us to accurately calculate and monitor extractions in the valley. And so in this graph, you're seeing from left to right from the year 2000 to 2019. On the left axis, we're looking at volume of water extracted from the basin going up to 70,000 acre feet, although 60,000 is about the high mark that we hit. On the right axis, and coming down from the top in the green bars, is annual precipitation by calendar year. So obviously, the more precipitation we have, we tend to see a decrease in groundwater pumping, and then on those drier years, we see an increase in pumping. The dark blue is the agricultural water use, the light blue is all the other water use, and the purple is what we would call our agency supplemental water supply, which is largely recycled water, but also includes water that's recovered from our managed aquifer recharge and recovery projects. We average about 50 to 55,000 acre feet a year, and looking at this graph, we can see in the most recent 5 or so years, we are doing better in terms of producing less water, and especially less groundwater, than we did at the beginning of the century. Through time, our groundwater levels in the basin fluctuate, and they fluctuate on a cyclical basis each spring and each fall. So I'm going to take the next 4 slides and not spend a lot of time on them, but just kind of walk you through so you can see how the groundwater basin looks. This is following drought, so we're sort of starting off in one of the worst places where we have groundwater elevations below sea level, as shown by these red contours, all the way back to the San Andreas Fault. The blue contours are where we have water levels that are above sea level, so those areas that are recharging the groundwater basin. And we see as groundwater extractions go into the fall through the peak agricultural season, we hit our lowest levels. And then in the spring, this is the spring of 2018, we see much recovery. This is after the drought was over and we had a couple good rain years. And wells are off in the valley, which is easing the pressure, stresses on the aquifer. Then in the summer of 2018, with most of the wells running, we've decreased the pressure in the aquifer, and water levels have dropped. And then when the wells turn off, the pressure begins to increase again. That coupled with recharge, we see we've recovered almost entirely with no red marks on this map. So this is the spring of 2019, and this is what we're shooting for each and every year. And then here we are in the fall of 2019, and where these contours go through, this is recharge through the Pajaro River, and in the north we have recharge through the Corralitos Creek area and recharge through the Pajaro River here. Seawater intrusion has been occurring, and it was first documented in the 50s by a report published by the state. One thing that's important to note, because coastal basins don't always show their seawater intrusion chloride contours using the same value, we show chloride concentrations at 100 milligrams per liter. And so this is 100 milligrams per liter through time, drawn in 1951, 66, 98, and then in 2017, there's just a tiny little increase compared to what we had seen in 2011. That is, that's what we can measure. And measuring seawater intrusion is a challenge because it's occurring in the subsurface, and we, for instance, have monitoring wells around the valley, and if one well is contaminated with salt and another one is not, we don't know where between the two wells the seawater intrusion front may be. New tools are being developed all the time to help water managers identify these things, geophysics, for example. But those have challenges too because of all the metal that's used to irrigate the agricultural fields. what have we been doing to manage seawater intrusion, which has been the result of long-term, multi-decadal groundwater overdraft? One of the things we've done was developed, this is actually our third hydrologic flow model, but this one was developed in the public sector code of mod flow under the oversight of a technical advisory committee that was designed to mimic the use and movement of water all throughout the Pajaro Valley Basin. And then we can simulate the past reasonably well, and we can use it as a tool to predict the future and to predict how various water management strategies might work to affect our goals of eliminating seawater intrusion and overdraft. So through the modeling effort, it was determined that what we needed to do was work to reduce groundwater extractions in the coastal area while also reducing groundwater extractions throughout the whole valley. And part of the agency's Enabling Act requires us to work to maintain agricultural activities. So we can't just go and say, you know, you can't grow crops on these fields anymore. We're trying to find supplemental water supplies. We're developing them to provide to growers in the coastal area that they can maintain agricultural activities while at the same time reducing groundwater extractions. And so when we can deliver water to the folks that are shown, for instance, in this map in the purple area here, is what we call our delivered water service area or delivered water zone through this series of pipes. The water that they take from us is essentially water that they don't need to pump out of the groundwater basin, and we call that in lieu recharge. The types of water that go into our project, into our pipelines, include our Harkins Flue facility, which I'm going to dive into in more detail in the next few slides. This facility has been was constructed and operational since 2002, and we've recharged 10,000 acre-feet since then. The purpose of the facility is not just to recharge the water, but to extract it to use as our pipes to offset groundwater production. The recycled water facility became operational in 2009 and has been a great drought-tolerant supply of water, and we continue to work to improve it. And then we now have built more than 21 miles of pipeline along the coastal area that can service approximately 6,000 irrigated acres of farmland. The Harkins Flue facility itself includes about a 15-acre area that the agency purchased, and 7.5 or 8 acres or so is for infiltrating surface water that we divert from a stream called Harkins Flue that's not too far away. In fact, in this figure, this yellow circle here, the small one, that's where the point of diversion is on Harkins Flue. And if we don't take the water from there, the water will follow this red line down through the rest of the Watsonville Flue system, have a short stint in the Pajaro River before flowing into Monterey Bay, where, you know, it mixes with seawater and provides no more use for us. So instead, we run the water through a filtration facility to knock out the turbidity and send it to the recharge basin, which is shown in the picture here above. Zooming in on the recharge basin itself, we have a fair amount of infrastructure around it. There are about, at this time, 13 or 14 monitoring wells, about 12 or so recovery wells. Some have gone into retirement. Some new ones have been constructed as we've learned more about this project. Initially, you know, and it was interesting, the initial studies found, doing subsurface investigation, that the lithography was fairly homogeneous soil, but minor discrepancies in the sand to silt ratio make a big difference in our ability to infiltrate and recover water, as we'll see. In the little cartoon image here in the lower left part of the figure, courtesy of Andy Fisher, thank you very much, Andy, we see that when we put water into the basin, it mounds in the subsurface in the shallow sands that underlie this recharge basin. And I should say that the San Andreas Terrace, where this is located, is all ancient sand dunes, aeolian deposited sands, very fine to medium grain sands, interdeposited with some silt and little bits of clay. And there's a large clay that exists right about sea level that serves as a floor for the recharge water. Through time, we've recharged about 10,000 acre-feet. However, we've only recovered about 1,000 or almost 4,000 acre-feet. And so what we're working to do is try to close the gap between these two lines here. We watch through a series of monitoring wells, the water levels in the basin go up and down each year with the amount of water that we recharge into the basin. So each year you can see in this blue line on the top of the graph, the recharge water, the response in the shallow monitoring wells, and the response in the lower regional wells. And you can see that they're not connected. Similarly, this is our recovery wells and our monitoring wells in this slide. And what we noticed was that some of the recovery well water matches the monitoring wells, but some don't. And so we spent a lot of time investigating what's going on here. In a collaboration with Stanford University, we put in some pore pressure sensors to kind of look to see what is the effect. Can we track where the water is going? Using 5 or so different points, we put in these resistivity probes. And what we found was that there is a silt layer about 40 or so feet below the ground surface that has a larger effect on our ability to infiltrate water than we anticipated. We decided to put a pressure sensor just below that silt layer to see the effect. And these two boxes here that are shown, they indicate, one, this one where the green arrow is showing, that as the blue, which represents recharge activities, occurs, the pressure sensor, which is located above the silt, feels the response of the water level. However, over here where the pore pressure sensor is just below the silt, there's very little response of the pore pressure sensor, indicating that the recharge water is not penetrating through that silt layer. That was problematic. So what that led to was us to develop some new recovery wells that would be screened both above and below the silt layer, as shown here in this graph. And in this case, the silt layer is right up here. And so we put the screens both above and below in hopes that we could let water from the upper layer recharge into the lower layer, or have water be able to pump from the aquifer as a composite rather than one part. In addition, we've done some work with the university, and Andy and his team have looked at the effects of denitrification. What is the effect of water quality as the water goes through the recharge basin? And they also looked into how does infiltration in the shallow part of the basin, the first 3 or so feet below the basin bottom, change through time. And there's been some really interesting results from that work that's been published, it's almost been a decade ago now, by Calla Schmidt and Andrew Rays. We've done our own subsurface investigation as well, and we've found that the complexity of the hydrogeology is more well-defined at this point, and that's important because we're looking to construct additional recharge basins as we go. And so we see the sand, we see this brown clay or silty clay that was problematic, especially noting that this gravel layer right here is where most of our recovery wells were attempting to recover water. The problem we've had is that the recovery wells are here, yet the water is recharging here, and this clay, depending where it's located, can be problematic. And here's just another example of that clay, and it's not uniform and it changes in thickness, and so it's taken some time to figure out what's the best way to put in new recovery wells and to both recharge and recover water as efficiently as possible. We also look at the quality of the water through time. We monitor the chloride concentration. We also monitor the nitrate concentration. And importantly, during the drought, when we cannot recharge water, we see the nitrate concentration in the shallow aquifer start to spike. But then the year that we recover from the drought and we can infiltrate surface water again, we see a significant decrease. And then we went through another dry period where we weren't able to recharge, and then we recharged again and saw another significant decrease. So recharge has other benefits besides just adding water to the basin. It improves water quality in the basin. And then just to wrap it up, I've got a few slides here to show the effect of all these projects. Through time, we've seen that the amount of water we're delivering is actually starting to exceed the amount of water that's being pumped out of the coastal area of the basin. That is really important, and that's the effect of our projects and the long-term goal to continue reducing groundwater production, as shown in blue, and increasing supplemental water supplies harvesting surface water, recycled water to keep agriculture in production while reducing coastal extractions. This has also been shown the effect of it in monitoring wells in the coastal area, where we've seen prior to project operations, water levels were declining and chloride concentrations were increasing. We started delivering water in 2009, and we got the water levels above sea level for the first time in a long time. And then even during the drought, while water levels declined, they didn't go back to where they were pre-project. And when the water levels are coming up, we're also seeing an improvement in the water quality for this basin. So that's another proof of concept. And then lastly, was a study done by Meredith Goebel, who earned her PhD at Stanford University under Rosemary Knight in geophysics. And their geophysical survey of the coast showed that the area where we've been delivering the water the longest was fresher in quality than the surrounding area. So in this color map here, the darker the blue, the less salty the water, and the deeper the red, or the warmer the colors, the more salty the water. And so that's been a positive benefit from this project as well. So the projects and programs are working, but they're not enough to stop the problems of seawater intrusion. One of the things we've done was we just this year built a new pipeline to extend our delivered water service area further to the north, where we can help to reduce seawater intrusion in that area where it's carrying above our delivered water service area. And we're working to plan new water supply projects. So I talked about this planning committee that met in 2010, and their job was to figure out the next set of projects and programs. They decided that we're going to conserve water and find about 7,000 acre-feet of new water through either optimizing our existing facilities or developing new facilities. And so this map sort of shows where the facilities would be located. We're looking at surface water at College Lake, and we're looking at a sister project to the Harkins Slough facility that would be on Struve Slough to divert more wintertime runoff. This is what this shows here. This is the Watsonville Slough Managed Aquifer Recovery Project. It includes some projects to improve the existing Harkins Slough facility. We have a water right permit application in for a new point of diversion on Struve Slough, where we hope to be able to one day divert and recharge and recover up to 4,000 acre-feet of water. And then we're working hand in hand with the University of California, Santa Cruz, with Andy Fisher, and with the Resource Conservation District of Santa Cruz, and also with landowners in the Pajaro Valley, to find ways to infiltrate water on private land. And the agency provides a financial incentive to make this more appealing to the landowners. And you'll hear more about that. With that, I will conclude my presentation, and I'm happy to take comments or questions when we get to that point.